All right, cool. Thank you. So, good morning, everyone. Today we'll be talking about how Apache Spark works from both a developer and an operations perspective. I'd like to start by mentioning that this slide deck is being released under a Creative Commons license, which allows everyone to download it and share it as long as you don't use it commercially. You should be able to see that link, but I'll read it to you. If you go to training.databricks.com/devops.pdf, then you can download the slide deck. So once again, that's training.databricks.com/devops.pdf. And it's probably about a 15 megabyte file. Yep, training.databricks.com/devops.pdf. And also, this talk will be on YouTube in about 2 weeks, so you don't have to worry about taking notes. There'll be a massively long video, like a 6-hour video, that will be uploaded to YouTube soon. So as you're downloading the slide deck, I want to mention that the idea here today is to give you a peek behind the scenes of how Spark operates. So we're going to be linking the user-facing developer API to how Spark code executes in a distributed way in the cluster. And there's also a LinkedIn link there if you want to connect with me on LinkedIn. So to begin, I want to mention that I work for a company named Databricks. And this is a company that was founded in late 2013 out of the UC Berkeley team who invented Spark. We have about 55 employees, and we are hiring. If you would like to work on making Spark even faster, then please look at some of our openings. And what we do at Databricks is not only do we contribute very heavily to the open source project, but we have a end-to-end hosted platform called Databricks that lets you run Spark code through the browser, and it's connected by in the background to an Amazon cluster. So the goal of our product is to make it be the easiest place to be up and running with Spark with little or no upfront hardware investment cost. This is a little bit of information about the team. And this is roughly the agenda of what I would like to cover. So in the first hour or so, we're going to kind of quickly move through some historical perspectives about Spark and big data, and then also kind of quickly move through the RDD fundamentals section, and then jump into the Spark architecture. And then we'll also cover GUIs for Spark, and there's roughly a 30-minute lab I have for you guys this morning. And in the afternoon, we'll go even deeper into how Spark operates by covering things like memory and persistence, talking about how a Spark application breaks down into jobs, which break down into stages, which breaks down into tasks. We'll cover broadcast variables and accumulators pretty quickly, and then cover the PySpark architecture. And I have a kind of cool section on shuffle and streaming as well. So in general, this is going to be a very fast-paced, vendor-agnostic, and very technical class on Spark today. So here is a little bit more about the class setup. I have a lot more slides than I'm going to be able to cover. This is actually a slide deck that I pulled out of a 3-day class that I developed at Databricks. So instead of removing all of the slides, I kind of kept a lot of the extra ones in there. I would like to encourage us to keep the Q&A relatively short and low, because there's a lot I want to cover, and I want to move fast. And if there are questions that you have, I will hang around the podium from like 5 to 5:30 today, so you can feel free to ask me questions one-on-one. We'll do 2 surveys. One of them has already been done. Most of you guys did the survey already that was emailed out. If you have not done it yet, then I would encourage you to do it in the next 10 minutes or so. There will also be another survey around 4 p.m. to just get your feedback about the class today. We'll take lunch from noon to 1, and we'll take 2 breaks. I'm not exactly sure when, but probably about an hour and a half from now we'll take the first break, and sometime in the afternoon we'll take the second break as well. So a little bit of information about me. I'm a client services engineer at Databricks. I do training, consulting, and a little bit of tech support as well. So a lot of the customer-facing aspects. I spent about 2 years doing freelance big data consulting and training. I taught many classes on Hadoop, HBase, Cassandra, Couchbase. And before that, I used to work at Hortonworks and Accenture R&D and Symantec. And you can see some of my hobbies there listed at the bottom. If you do run into me in the hallway, I'd prefer to talk about the last 2 lines in this slide, probably more than all the lines above it. So that's a trick to get me to be able to answer questions for you. All right, so that's a little bit about me, but I want to tell you guys a little bit about yourselves. So as of like 2 days ago, 89 people had completed that survey that was sent out via email out of the 215 that registered for the class. So this is a decent sample size. And you can see here that almost all of you guys are developers. That's about 90% of you guys identified as developers. There are some overlap. Some people consider themselves a developer and a data scientist. And nobody here really identifies as being purely an admin. And I think maybe 1 or 2 people might be in the wrong class. All right. And where are you guys from? The San Francisco Bay Area draws about 25% of the audience. About 12% are from California, but not the Bay Area. So more than 50% of the people in the class are from either California or the West Coast, or the west part of the US. And actually, about 75% of the audience here is from the US in general. And you can see there's a few people here from Europe and Asia and other international countries as well. These are the industries you guys work in. Most of you guys work in IT or systems type of work. Some people more in like science and technology research type of stuff. Prior Spark training. Almost no one here has taken, I guess, professional Spark training before, so it'll be most people's first time. And this is an interesting slide. How much hands-on experience do you guys have with Spark? So this is going to like kind of help me calibrate how fast I move and what topics I cover. So 6% of people are being exposed to Spark hands-on for the first time today. A total of about 20% of people have less than 1 week of hands-on experience. And more than 50% of the audience here has less than 1 month of hands-on experience. So you guys are relatively new to Spark. I'm going to assume that you guys have kind of looked at some transformations and actions. You've been at the shell. You might have also looked at the Spark UI. So I'm not going to cover those things very much in depth. I'm going to kind of go beyond that. And most of the rest of the people, about 43% of the people, have 1 to 6 months of experience. I think almost no one said they had more than 6 months, or very few people. Where are you in the Spark usage lifecycle? A few of you guys are just reading about it right now. That's 10%. And then 20% of you guys have like a 1-node VM kind of running, that, like a toy cluster you're playing with. And 50% of the audience is actually setting up a POC or prototype. So I think this class will be actually very, very relevant to especially this segment of people. And about 15% of you guys are in production. What about programming experience? So we'll kind of quickly fly through these slides. You can see that a lot of people are getting into Scala. So you guys are identifying, 50% of you approximately identify as beginners in Scala. But you, in general, identify as medium or expert in Java. And you can see that some people here, like 15%, have no experience in Scala, and about 12% of people here have no experience in Java. What about Python and SQL? About 25% of the audience here hasn't really hacked in Python at all. You guys seem to be more of like a Java crowd. Only 13% identify as expert in Python. And in SQL, people seem to kind of know SQL relatively well. A lot of experts and medium level people. And R is a new API that was added in Spark 1.4. And this is not a data science class, so therefore I also anticipated this outcome that about 70% of the audience here doesn't have really any hands-on experience with R. This next slide is actually perhaps the most interesting one for me. This is how much knowledge you guys have about the other big data systems. To me, this is kind of a, I can extrapolate from this maybe the adoption of some big data systems. So HDFS and MapReduce, about 75% of you guys feel relatively comfortable with. You said you had medium level experience and hands-on experience with HDFS and MapReduce. You can see that some of the more popular projects like Yarn, Kafka, Hive, Cassandra, HBase, Zookeeper, Pig, some of those kind of show up a little bit higher up as well. And you can see the actual percentage here for the how many of you guys had medium level experience. And I believe this is the last slide for the survey results. What did you guys want the focus of today to be? About 65% of you wanted the focus to be development. And this is really high. About 85% of you wanted the focus to be administrator and ops and architecture. This is interesting to me because you guys are almost all developers, but you wanted the focus of this class to be more architecture and administration. So it's neat. OK. So now we'll get into kind of the historical slides, and I'm going to move quite fast here so I can get to the technical material. So Spark comes out of UC Berkeley's AMP lab. And the AMP in AMP stands for Algorithms, Machines, and People. There's 3 dimensions that AMP Lab focuses on to improve data analysis. Algorithms are for they're trying to improve the scale of algorithms and the efficiency and quality of algorithms. Machines are meant to scale up in data centers. And the people aspect is for leveraging human activity and intelligence to augment the algorithms. You can see that AMP Lab was launched in January 2011 with a 6-year planned duration. There's about 65 people involved in it and funding from 20 companies. Mesos is perhaps the first famous project to come out of AMP Lab, and Spark is perhaps the second other famous project to come out. So I want to frame Spark in a certain way in the big data world. So for the longest time, big data was about storage. It was kind of about pulling your data perhaps out of Oracle or MySQL farms and denormalizing the data and changing the schema perhaps and putting it in a NoSQL database. And that's what I spent actually a lot of the last 4 or 5 years doing myself. And you can see the battles there were like, first of all, they were just relational versus NoSQL. It was like that was going on 5 years ago. And more specifically within the NoSQL world, there were like little battles being fought in certain categories, like HBase versus Cassandra, Redis versus Memcache and React. And you can see these are the key document databases, graph databases, search type of databases, or search engines. And what's happening now is Spark is not a NoSQL database, right? It's a computation engine that can read out of essentially any relational or non-relational database. So I want to kind of frame today as being like right now we're in the era of processing engines being duked out, I guess, or being really a lot of the hyper innovation is happening more in the processing layer these days. So if you look at kind of who might have won in the NoSQL side, these specific names on the left that are red kind of won those specific battles. I'm sorry if that's kind of hard to read, but hopefully you can kind of follow along with the PDF as well. So relational and non-relational both kind of win, right? Because NoSQL never really was meant to replace all of the relational use cases. And how did I even choose that? Why would I say that maybe Cassandra might have done a little bit better than HBase? Well, because of this. There's this website called dbpopularity.com, And DB popularity essentially tries to understand the popularity of databases by doing things like looking at how many LinkedIn profiles mention a database, how many job listings on Indeed.com, for example, mention a specific engine, looking also at Google Trends. So DB popularity is not looking at the actual adoption of these systems, but it's looking more at other things, like how, on discussion boards, which names show up more, like on Stack Overflow. So if you look at it like that, I'd like to recommend that, like, if you're going to use NoSQL, the first thing to do is really to decide what type of NoSQL system you need to use. Do you need to use a key value or a key document, a column family, a graph, or more of a search engine type of system? And once you do that, then you can go to DB popularity, and you can see that Redis has a popularity score of 95, and it leads in that category, whereas Memcache is a second place contender at about 33 for popularity. MongoDB has about 300 as a score system for key document, and CouchDB is at about 28 for popularity. Cassandra is at about 110 for popularity, and HBase is at 62. This is interesting because HBase was like 2 or 3 years ago was slightly more popular than Cassandra. And in the graph category, Neo4j just kind of dominated, and it's got 30, versus the second place is OrientDB at 4. And in the search, it's interesting. In search, it's kind of evenly spread. Solr has 81, Elasticsearch 70, and Splunk 41. All right, so another way to think about Spark is originally there was just MapReduce, or it was by far the most popular engine. And in the last few years, a lot of competitors have arisen in the processing arena to compete with MapReduce. These specialized engines emerged, like Giraffe for graph processing, Impala or Drill for more SQL type of processing. Mahout is this machine learning library on top of MapReduce. But the problem here was that it became very complicated very quickly. So now if you wanted to do some realistic production type of big data use case, you have to not only figure out how to use perhaps 2 or 3 NoSQL databases to each store different classifications of data, but now you also had to start learning different computation engines. And it was a lot of cognitive overload for programmers. And what Spark tries to do, one of the motivations behind the Spark project was to give developers a unified engine to be able to do batch analytics, graph processing, machine learning, and real-time queries. So now a team of like 2 or 3 engineers can do what might have taken 10 engineers to do before. So this is going to start introducing some iconography for today, because we're going to kind of see these icons repeatedly throughout the day. So at the center of the Spark universe is Spark Core. And Spark Core uses both memory and disk while it's processing your data. And around Spark Core, there are 4 now APIs. There's a native Scala API, there's a Java API, a Python API, and as of a few days ago, there's a R API. And data frames is this concept that kind of unifies all these APIs. The data frames API was inspired by data frames in R and pandas in Python. And data frames will give you state-of-the-art optimization through the Spark SQL Catalyst Optimizer. And we'll cover data frames a little bit more later today. And next is Spark SQL. So now we're looking at the next level up. So we're looking at some of the higher level libraries built on top of Spark Core. So Spark SQL is the module for working with structured data made of rows and columns. Spark SQL used to work against a special type of RDD called a schema RDD, but that's in general being replaced by data frames now. Spark SQL reuses the Hive front end and Metastore, which gives you full compatibility with existing Hive data, queries, and UDFs. So it lets you run unmodified HQL queries, Hive queries, on your existing data warehouse. Spark SQL can be seen as almost like a drop-in replacement for Hive. There's also standard connectivity through a JDBC or ODBC driver from Simba. And some applications like Tableau, for example, use that Simba driver to send queries down into Spark SQL to run at scale. The next project I want to mention is Spark Streaming, which lets you analyze streams of data coming in to your big data system. And the cool thing about Spark Streaming is it lets you reuse the code that you wrote for batch processing in streaming as well. And to give you some metrics about Spark Streaming, in 2012, so that's like 3 years ago, Spark Streaming was able to process 60 million records per second on a 100-node cluster at sub-second processing latency. So this makes Spark Streaming, at least even in 2012, it was 2 to 4 times faster than some comparable systems like Apache Storm or Yahoo's S4. And Netflix is one of the big users of Spark Streaming, and they're trying to contribute code to it as well. So once again, that metric was, in 2012, it was able to process 60 million records per second on a 100-node cluster. There's also machine learning libraries, and we're not going to cover that too much in class, but MLlib is Spark's machine learning library, and GraphX is kind of a component within the machine learning arena of Spark. And there's a lot of different things happening in machine learning. It's one of the most active parts of the Spark code base. And I would encourage you to watch Reza's YouTube video, which is being recorded as well. And he's covering all of only machine learning in his class. All right, BlinkDB is a really interesting project. And eventually, the work going into BlinkDB will be slipstreamed into Spark SQL. So what BlinkDB does is it's an approximation query engine for running SQL queries at scale. It allows users to trade off the accuracy of the answer by getting an answer quicker that is less accurate. So I'll show you a few more slides about BlinkDB as well. But the idea here is perhaps you have terabytes and terabytes of data, and you want to do some query on it. You want to get the average age of your users, because one of the columns you have is age, and you want to get the average age, but you don't want to go through all of your data, which might take a while. You just want to get quickly what the average age is, and you're OK with the 10% error bar. So BlinkDB can do something like that for you. So BlinkDB was demoed in 2012 on a 100-node Amazon EC2 cluster. And in this 100-node cluster, BlinkDB was answering a range of queries on 17 terabytes of data in less than 2 seconds with an error bar of 2 to 10%. That makes it roughly 200 times faster than Hive. And to do this, BlinkDB uses offline sampling to create uniform and stratified samples of the underlying data. And 2 of the users of BlinkDB, for example, are Conviva and Facebook. Tachyon is a memory-based distribution storage system that allows you to share data across cluster frameworks like Spark or Hadoop MapReduce. Perhaps you already have a bunch of ETL code that you wrote in Hadoop MapReduce, and you want to leverage your existing work. So what you can do is you can continue running that existing work, and then at the output of that MapReduce job can write something to Tachyon, which is basically a memory handoff to Spark, which will then read it out of Tachyon and continue processing it in memory in Spark. So Tachyon has about 60 contributors from 20 institutions. It has a Java-like API similar to the java.io.file class, and it provides an input stream and output stream interface. And Tachyon also implements the Hadoop file system interface. The next third layer out is resource managers. So we'll cover this quite in depth later today. But essentially, you can run Spark in local mode. That's the icon at the top. Orange is a laptop. That's kind of like just running on one JVM on one machine. And on the far right, that's a ball of yarn, because yarn doesn't have a existing logo. That's what I found. So every time you see that, that implies yarn. And underneath that is Mesos. Mesos stands for mediator in Greek. And Mesos is similar to yarn, which is also kind of similar to standalone mode. All these things are doing, yarn, Mesos, and standalone, is they're starting executor JVMs for your specific Spark application. So if you want to learn Spark, essentially Spark is just a driver JVM which is like the head of your application, the brain of your application. And that driver JVM has like dozens or hundreds or thousands of executor JVMs that actually do the work. And that is really your Spark application. It's a driver and a bunch of executors. These resource managers, they just help you start your executors and make them highly available. But they all do the same thing. They just help you start the executor JVMs. Once the executor JVMs have started, they register directly with the driver, and the resource manager is not really in the control loop anymore. It's just kind of there to make the executors highly available in case they crash. All right, and Zookeeper can be used to make all those resource managers highly available. All right, at the final outer layer, on the far left are file systems like HDFS, Amazon S3, which is an object store, OpenStack Swift. Spark can also read from ext3 or ext4. Spark can read from, these days, almost every relational or non-relational database. Anything that has a Hadoop input format interface, Spark leverages and can read from. So one of the very common use cases I see for Spark is basically doing joins across disparate data sources. Kafka and Flume can operate like buffers to Spark streaming. And there's many distributions for Spark these days, and there's a lot of applications as well that leverage Spark in the background without you even knowing you're using Spark. Things like Zoom Data and Click and Tableau, for instance. Okay. So Spark currently has developers contributing code from more than 50 companies. There's more than 400 developers. And the committers come from 16 different organizations, the people who can actually merge the pull requests. So a very common question I get asked is, what about Hadoop versus Spark? You know, is Spark supposed to replace Hadoop, or like how does it fit in? Can I just spend 3 years learning Hadoop? Can I leverage my Hadoop knowledge, or are you going to keep doing this and keep coming out with new engines? Well, first of all, I want to mention this is a technical class, so I want to clarify that Hadoop has kind of taken a marketing term of its own, which I don't want to cover here. To me, Hadoop is 3 things, because if you look at the Hadoop code base, Hadoop is 3 Apache projects, essentially. It's Hadoop MapReduce, Yarn, and HDFS. And if you compare that to Spark, Spark Core is the leading contender, perhaps, to replace the MapReduce engine in Hadoop. Now, you can see with the Mesos, there's basically the line going back and forth. You can continue using Yarn and run Spark on top of Yarn. If you're building a new system from scratch, perhaps you'll use Mesos as your resource manager, or you'll use Yarn. A lot of times, this decision will be dictated by which vendor distribution you're using. For example, the DataStax distribution does not use Yarn or Mesos. It uses a standalone scheduler. At Databricks, we also use the standalone scheduler. Some Hadoop distributions like MapR, Hornworks, and Cloudera use Yarn. So that will not necessarily be a choice you'll make unless you're building your stack completely from scratch. And then HDFS doesn't get replaced really by Tachyon. Tachyon is an in-memory file system that you can use even if you're still using HDFS. And now there's other projects in the Hadoop ecosystem like Hive, Mahau, or Storm. And Spark has like some corollaries to that. For example, you can take your Hive queries and run them under Spark SQL. Mahau even made an announcement 6 months ago that they are not going to be accepting MapReduce implementations of machine learning algorithms anymore. They're now moving completely to Spark implementations and rewriting some of the existing ones to Spark as well. So the cool thing about Spark is since it has a unified API, you can learn like one set of APIs and kind of do all of these projects on the left under one set of APIs. Okay. One other thing about Spark, like why is it fast? Well, one way to think about this is in the MapReduce world, like for example, if you used Mahau and did k-means clustering, I did that once, and I think it decomposed down to 17 or so MapReduce jobs, and it took roughly, I think, 15 or 20 minutes to run against approximately like a 10 megabyte data set. Because there's just a lot of overhead in doing 17 MapReduce jobs. What do I mean by that? Well, in MapReduce, traditionally what people did is they had some input data in HDFS, and they would run one MapReduce job on top of it to do one phase of computation and write those results back down to HDFS, and read those results in a second MapReduce job, and to write the second MapReduce job's results down to HDFS. And you might do this in a loop or an OR again, each MapReduce job doing a slightly different task in your computational pipeline. And often people would use Apache Uzi to, which is an XML workflow engine, to schedule these MapReduce jobs in order one after another. So you'll notice this is a misspelling of Uzi. Uzi is actually, I think it's spelled U-Z-I, and it's an Israeli subatomic machine gun that shoots bullets in order. And somewhat similarly, the Apache project Uzi shoots MapReduce jobs in order into a cluster. And it's misspelled because if you search for Uzi like this, you will not end up learning a lot about machine guns along the way. So how does Spark do this? Spark can still read from HDFS. If you have enough memory, it'll try to load that up into memory. And then it will start processing it and hand it off to a memory buffer for another Spark job or application to continue processing it. So the loop in Spark is usually within memory. However, Spark will gracefully degrade down to spilling down to disk if it needs to. So if your data set doesn't fit in memory initially or during your computation, maybe the data explodes, that's not a problem for Spark to handle. And you can write the output to wherever you want. In this example, it's going to Cassandra. So this is one of the reasons that Spark can be 10 to 100 times faster. It's especially when you start taking your old built MapReduce pipelines, and which had maybe 20 or 30 MapReduce jobs, and you replace that with Spark. That's when you get closer to like the 100x increase in performance. This is just some historical information about Spark. Spark was open sourced in 2010. Actually, the newest figure I have is there have been about 700 total contributors to Spark so far, who have contributed a total of about 400,000 lines of code. And there's roughly 500 active deployments that we know of. There's probably a lot more in the wild. Spark is the most active Apache project according to contributors per month. You can see here that, so this is just saying that there's roughly 300,000 lines of code, but like I said, the more accurate number is 400,000. It's mostly written in Scala. About 75% of it is Scala, 7% Java, and about 10% Python, and 8% is other languages. I believe there's like some Fortran deep inside MLlib somewhere. This is the number of contributors per month. This is the lines of code being added to Spark. And you can see like a steady growth in the blue is code, black is comments, and green is blank lines. And you might be wondering what happened here. There's a dramatic drop in the lines of code in Spark. So what happened there is people noticed, I think Matej told me, I got to ask Matej, I was like, Matej, what magical thing happened that you reduced the lines of code like that? And he told me, well, he discovered that somebody had dropped a big data file in the repository. So as soon as they deleted the data file, then the lines of code got cleaned up. So that's what that was. OK, so why is Spark so, why is it so into using memory? Well, if you need to move data between memory and CPU, the native bus in modern computers moves it at about 10 gigabytes per second. As soon as you drop down even to an SSD, you're down to 600 megabytes per second. So the more you can leverage memory and store your data in memory while Spark is processing it, the faster your computation will be. And as soon as you go down to magnetic disk, you're looking at roughly 100 megabytes per second. Once you go over the network to another machine, you also drop down to about 125 megabytes per second. If you go to another rack, you go down to about 0.1 gigabits per second. All right, so I'm just going to really quickly mention that there are several papers on Spark. The original paper is from June 2010 called Spark Cluster Computing with Working Sets. But I would actually encourage you to not necessarily read that one, but read this one. the RDD paper from April 2012. This kind of builds upon the previous paper by repeating a lot of the information from the first paper, but a lot more information is in this paper. This is a 13-page paper versus the one from 2010 was 6 pages. And I've highlighted some things here that are interesting from this paper. There's also a Spark streaming paper that lets you analyze streams of data in batch intervals as small as half a second. We'll cover Spark streaming later this afternoon at the end of the day. Spark SQL lets you mix SQL queries along with your Java, Python, R, or Scala code. There's GraphX that lets you analyze nodes and edges using graph processing. You can see a small example there. So GraphX essentially unifies ETL, exploratory analysis, and iterative graph computation within a single system. And the processing in GraphX takes some inspiration from the Pregel API, if you've seen that. There's also a paper on BlinkDB, and you can now start seeing some of these SQL queries for BlinkDB. They're just select statements, but you can see on the left here that it's asking for a return for the select statement within 2 seconds. Or if you don't want to bound BlinkDB with time, you can bound it with a error bar, and you can say take as long as you want. But once you are, within a 5% confidence interval, let's say, you're 95% confidence that your error bar is 0.1 within 10% error, then give me the answer. So the idea here is like if you run this query and say, come back within 2 seconds, the results will come back in 2 seconds, and it'll say, this is the error bar right now. And you might look at that and say, oh, well, you're saying that you might be off by 15% right now. And I would rather you just take as long as you want, but come back and tell me the answer once you're within a 5% confidence interval. So anyway, a lot of this work will be going into Spark SQL later on this year. So a little bit more insight into BlinkDB. The idea here is, so you can see the y-axis is the estimate, and the higher up you go on the y-axis, the closer you get to the true answer. And on the far right, on the x-axis, is the number of data points. That's how much of your data are you computing in. And you can see that what happens is that the closer you go to the right on the x-axis, the error bars go smaller, get smaller. But perhaps it'll take longer for you to get there. So the idea here is BlinkDB lets you say when you want to stop processing more data because you're close enough to the final answer. So you stop when the error is smaller than a given threshold. And you don't control this by saying, BlinkDB, go through this much data. So you don't control it by number of data points, but more on a time or error confidence interval. All right, there's a book on Spark from O'Reilly that I would highly recommend. There's many different digital versions of it. And if you go to Amazon, actually, it's a little bit cheaper. And this book, as of a few days ago, had 19 customer reviews on Amazon and had a 4 out of 5 star rating. It's a very good book. And there's also a more advanced book about machine learning and MLlib with Spark. This is also shipping now, and you can get it for a little bit cheaper on Amazon as well. OK, there's also a user mailing list on Spark where you can ask questions. You can go to this Apache Spark website and subscribe to the mailing list. It's very active. Some tips here are when you're asking a question, try to be as concise as possible and try to give as much log information and information as possible as well. So even though your question might be very succinct and concise, if you can have attachments or some additional information at the end of the email about the details, that would be very useful. One of the main things I want to point out is if you can mention which version of Spark you're on, that's very useful. And if a resource manager is where you think the issue is, then do mention which resource manager it is. But definitely the version of Spark, because Spark is moving very fast from a code-based perspective, and things are sometimes different in different versions. This is a reference slide. If you are planning on using Cassandra and Spark, like last year I made a 100-page lab on DataStax Enterprise 4.6. And if you want to see how to use Spark with Cassandra, you can check out this lab. This is not the lab we're going to really do today. There's also a lab I made last year that's about 100 pages on using Hadoop and Spark. And you can see that basically this first lab goes into a little bit of like Spark streaming. And it's a DevOps type of lab, so it shows you some things about development, but also configuration settings and administrator settings. And this is a lab on basically just learning about Hadoop and Spark. Even though it's on the Cloudera distribution, it's mainly about just understanding Yarn, Hadoop, and how that works with Spark. And the focus here is also for beginners and developer and ops administration, but it also goes into PySpark, Spark SQL, and shows you how to use Spark Submit in this lab. Once again, a reference lab that you can check out later on your own time. Spark Packages is a new thing. It's a website that is holds a community package index to track the growing number of open source packages and libraries that work with Spark. So what this does is it makes it easy for users to find, discuss, rate, and install packages. You can think of it like almost like an app store for Spark. Since Spark is moving so fast from a code-based perspective, we just wanted to give all people the ability to add complementary code that doesn't maybe necessarily need to be merged into the Spark code base. Maybe it's just a connector thing, like maybe a connector to a NoSQL database, and that might not really be appropriate to put into the Spark code base, but it should be in the Spark community, so that's why we created the Spark Packages website. So you should check this out, and especially if there's something that you don't think Spark can do right now, before you build it out yourself, you might want to check how many packages, or check through the packages to somebody else has already contributed code base for that. Or if you also make something that you think is kind of cool and you'd like to kind of get some visibility for your project, I would recommend submitting it to the Spark Packages code base. Okay, I want to do something interesting now. Since we are at a milestone of Spark 1.4 that just got released, I wanted to take about 10 minutes today and kind of cover what has been happening in Spark in the last year or so. So I'm going to just say a few things about what happened in the last 4 or 5 versions of Spark. And then after that, we'll start getting into some of the more technical things. So Spark 1.0 was released in May 2014, and it had about 117 developers who contributed to it. And this version of Spark brought many different features, but one of the main things it brought was a guarantee of core API stability across all of the 1.x releases. So when you write your code against anything with 1.x, you can rest assured that when you're using the core API itself, the transformations and actions, those will not change. And even when we go to 2.0, we're going to try not to change that even then. Spark developers take changing the API very seriously. And the way this generally works is when a new feature gets added to Spark, like Spark R, it's marked experimental for the first 2 minor releases, and then it's marked as stable after that. And that stable flag doesn't necessarily mean that it was totally like crashing or unstable before. Stable refers to the API. So after about 2 minor releases, a feature is marked stable, and then you can start writing production code against it and not worry about having to change the production code if a minor update happens to Spark. So the APIs are essentially marked as alpha initially, when it's kind of really in the R&D phase. Then it gets promoted to experimental for about 2 minor releases. And that's when you can start building your prototypes and POCs on it. And then it gets marked as stable after that. So this 1.0 release brought Spark SQL as an alpha component. It introduced support for Spark security, and it brought PySpark to Yarn. Spark Submit was added. So Spark Submit is a unified submission process for submitting an application to Spark across cluster managers. So you can write your app, like a Python or Scala app, and then you can use Spark Submit to submit it to either Spark running in local mode or standalone mode or Yarn. So it's a unified submission process, and your code looks the same regardless. Also, a history server was added so that you can, even after your application completes and the driver closes, you can still see the metrics of what happened when the driver was running. There were a bunch of improvements in MLlib, substantial performance boosts in GraphX, And Flume support was added to streaming, and there were a lot of performance optimizations done in Spark streaming as well. And finally, Java 8 Lambda syntax was added to be able to give developers a way to write concise syntax for writing anonymous functions. Okay, what about Spark 1.1? So you can see that the number of developers there was 117, May 2014. 1.1 was released about 3 months later, September 2014. 171 developers this time. A new sort-based shuffle was added for large-scale workloads where you have more than 10,000 reducers. Or essentially, you can think of this like when you are working with Spark RDDs that have more than 10,000 partitions, then you want to use the new shuffle implementation, the new sort-based shuffle, as opposed to the old hash-based shuffle. Other things were in Spark SQL, a JDBC ODBC server was added, JSON support was added in Spark SQL, UDFs came in as well. A lot of improvements in MLlib, and in general, 2 to 3x improvement in MLlib algorithms. Spark streaming started getting high availability across certain components. Kinesis support was added, a Flume pull model where Spark streaming can pull out of a Flume sink as opposed to Flume pushing into Spark streaming. Now we're also getting initial machine learning libraries being added to Spark. So streaming linear regression was added to Spark streaming. Currently there's 3 machine learning algorithms that work in Spark streaming. But back then, linear regression was added. In PySpark, support for age-based Cassandra and Avra was added. Okay, now we get 3 months later to December 2014. We've kind of stayed steady with the number of developers here. 60 institutions contributed to Spark 1.2. A new Netty-based shuffle network transfer subsystem was added. I'll kind of talk about what this does later. But this Netty-based network transfer subsystem is actually one of the main components that helped Spark win the 100 terabyte sort competition, which I'll also talk about later. Scala 2.1 support was added. In streaming, we got a Python API, driver high availability, write-ahead log. Spark SQL got a new external data sources API, Hive 0.13 support. GraphX graduated from being an alpha component, so it became an experimental component. And we also got a more stable API. Actually, no, it must have gone to stable, so it was probably experimental before. And PySpark started supporting broadcast variables greater than 2 gigabytes. These are the major highlights in 1.2. 1.3, now we're getting into this year, so March 2013. This is when the data frames API was released. Spark SQL graduated to become a stable API as well in 1.3. Core got a lot of performance improvements. There's now garbage collection metrics being reported in the UI. Streaming got a new direct Kafka API. And in PySpark, we got ML pipeline support. And now, finally, a few days ago, Spark 1.4 was released with contributions from 210 developers, even more institutions, about 70 institutions. You can see also that I've kind of given a special call out to also the institutions that have helped with benchmarking and integration testing. This is where Spark R was introduced. Spark R is the first release in a while to bring in a new programming API to Spark. There's a lot of cool things that happened in visualization in Spark. With a show of hands, how many people here have actually hands-on used Spark 1.4? Oh, quite a few of you, but not too many, about maybe 10% of the audience. So later today, I'm going to actually cover some of the UI improvements in Spark 1.4. I think that you'll find that really useful when you try to understand how your job is breaking down into stages and tasks. Before, you could only do that RDD called RDD and then .to debug string, and that was kind of hard to really dissect what's going on once you have like 20 or more RDDs in your DAG. But this new visualization stuff in the UI, it'll be much more easier for you to interpret what's going on behind the scenes in Spark. And you can see some of the other improvements here as well. Okay, so I do want to mention that, like I said, this deck comes from a much more comprehensive 3-day class that we developed at Databricks. And we are working on developing a lot of curriculum. We aim to have about 10 days worth of curriculum by the end of this year. So if you're interested in buying either our 3-day Spark Foundations class, which mostly focuses on Spark Core, then you can go to the databricks.com/spark/training website and just click that button. And if you fill that out, it drops an email in my inbox when you submit that form. And Databricks will contact you to talk about what you need for training. I also do want to mention that one of the people from our training partner is here. You can see Ben in the back. I'll ask Ben to raise his hand. If you are interested in buying a class from us, please contact Ben during one of the breaks today. And if you guys exchange business cards, we can do that as well. On the flip side, if it's not like requesting training, if instead I've blown you away and you just want to become a trainer, then you're welcome to do that as well. We are recruiting and hiring instructors to be able to deliver not just the fundamental Spark class, but a lot of the advanced material we're making as well. I would like to say that this is probably one of the best ways to really learn Spark. You'll get access to software engineers to really understand what's going on behind the scenes and help us develop curriculum. And we are planning on releasing all of the curriculum developed by our trainers into Creative Commons long term. Initially, we might keep it more closed just as we iterate the deck, but eventually we want to give our slide decks open source under Creative Commons. So the work you do, even though you might not be programming, will still be relatively open source. Okay, now we get into the technical stuff. So I'm going to fly quickly through this section, and then we'll take a break. This will be maybe a 15, 20-minute section. The reason I'm going to cover RDD fundamentals is because roughly 25% of the audience this will be quite useful for, some of the more beginner people, but also to introduce iconography once again, because we'll see this in the more advanced sections later. So when you use Spark, generally, Apache Spark, this is your interface. There's a REPL, a read, evaluate, print loop, which is interactive. So the reason the REPL is cool, and only Scala and Python provide this, and R as well now, but Java doesn't provide a REPL. And Java is not an interactive language. You kind of write your code in the IDE, you build your jar, and you submit it to the cluster. But then you wait for it to run, and then you look at the results. You don't get a feedback loop right away. In Scala or Python or R, with a REPL-like interface, you can write your code, and you can hit enter, and then it'll run really quickly in the background. You can see the results right away. So that's kind of cool. But what happens in the background is this REPL is essentially, this is what we are going to be calling our driver program, because it's backed by a JVM on your local machine usually. So this REPL is like your interface. It's like on your laptop. And you can run this driver program in the cluster as well. So you can like log into one of the nodes in the 100-node Hadoop cluster, and you can SSH into your machine, and then you can start the REPL there. What that means is you're just saying you're running that command to start the Spark shell in Scala or Python on that node in the Hadoop cluster, in which case now the driver JVM is running within your Hadoop cluster itself. But usually people will start the driver program on their laptop, and in the background there will be a cluster of Spark, and we're going to call these different machines in the cluster worker machines. I want to be careful about terminology. In earlier days of Spark, worker was a more loosely used term, where worker was either sometimes meaning the worker JVM, and sometimes it meant the worker machine. Anytime I say worker, I'm going to clarify what I mean by that. So to me, right now, I'm saying these are worker machines, or like slave machines. These are like the nodes in your cluster. You can see here also there is actually a worker JVM when you're running Spark standalone, but we'll cover that later. And we'll cover these actual JVMs later as well. What I want to do now is I want to talk about an RDD. I want to go to the logical way of looking at Spark. So RDD stands for Resilient Distributed Dataset. Here I have an RDD with 5 partitions. And you can see that each partition has 5 items in it. And this is simply a distributed collection of elements. you can think of this like kind of like a distributed collection, like an array or a list on a single machine, except it's spread out across multiple nodes in the cluster. And the items in the RDD can be images, it can be text, it can be numeric, it can be basically whatever type of binary data you have. And the more partitions you have in the RDD, the more parallelism you have. So what does that mean? Well, imagine that you have a 3-node Spark cluster with 3 executor JVMs. So the first RDD partition might land in that first executor. And maybe the second partition goes to the second executor, and those are the remaining 3 partitions. You can see how that RDD is now distributed across different executor JVMs. If you have a 100-node Hadoop cluster, or Spark cluster, and you have an RDD that's only 20 partitions, and you compute against it, you're not using all of your machines. You're only using 20 machines because you only have 20 partitions. So if you want to use all of the compute power in your cluster, you should have at least 100 partitions. But usually even more, because each executor can store dozens or perhaps 50 or so partitions, maybe more, depending on how much memory you have in the executor. So to really use all of your computational threads, you'll want to have, if you have in each executor the potential to run 7 tasks, let's say, so the num cores for executor is 7, then you want to have probably at least 7 partitions there in that executor for your specific RDD. So then that would mean a 100-node cluster times 7 would be 700 partitions. And if you have an RDD with 700 partitions, then when you compute it against that RDD, if you do a transformation on that RDD, it will actually use all of your threads. Now, the idea shouldn't be taken too far, because if your data set is only like 100, let's say it's like 100 gigs, you probably don't need to parallelize that much. At some point, there is diminishing returns. So another rule of thumb is that perhaps each partition should be somewhere between 50 megabytes to maybe 200 megabytes. This may be a good range for a partition size. Another way to look at this is when you're trying to figure out how many partitions you want in your RDD, in general, when you are computing against a RDD partition, if this is a 5-partition RDD, you would need 5 threads for this, 5 tasks. And in the Spark UI, it will tell you how long each task took to compute against this RDD. It will show you. It will show you 5 tasks, and it will tell you in milliseconds or seconds how long it took each task to complete. In general, you want a task to run somewhere between 100 milliseconds to maybe like a few seconds, maybe 100 milliseconds to like 5 or 10 seconds. If it's taking you a minute, then it might be a little bit too much. And if it's taking you only 30 milliseconds, you might need to put a little bit more data in your actual partitions. Another takeaway from this section is that when you look at those 5 threads, or those 5 tasks, and you see how long each one took, you might see lopsided behavior there. You might see that one task takes a minute, but the other 4 are running in half a second. That might imply one of 2 things. It's going to either imply that one of your partitions is significantly bigger than the other 4. So maybe you should repartition the RDD and equalize the data between the partitions. It could also imply that that one task that took a minute maybe had some issue with the hardware of that machine. There was perhaps a problem on the hardware, and therefore you should use the speculative execution feature in Spark to launch a clone of that task elsewhere, and if that clone task runs faster, your results will be given out of that thread, and the first one will be terminated. So something like Hadoop speculative execution, MapReduce speculative execution, something like that exists in Spark as well. However, the configuration settings and how it decides when it's going to kick off is a little bit different, how Spark does it versus how Hadoop does it. In general, in Spark, the way it works is it looks at like a median of how long all the tasks took to run. And after like 75% of your tasks have run, then it starts thinking, OK, do I need to kick speculative execution off or not on certain of the remaining 25% of the tasks? OK, now here's an RDD with 4 partitions. This specific RDD I've named log lines RDD. So like I've given it like a name in my REPL. So this is to me now called log lines RDD. And you can see that it has info, warning, and error messages. This looks like pretty standard pretty standard log file. It's an error and then a timestamp and an error message. And it looks like a CSV file, like comma-separated value file. You make RDDs one of two ways. You can either parallelize a collection or you can read from an external data source. When you parallelize a collection, what you're doing is something like this. In the REPL, in the Spark, like Python REPL, for instance, you're going to say SC, so Spark context, and on that you're going to call a method parallelize, and you just give it a Python list, and this list is going to go into making a words RDD. You can also put a comma here at the end, after the end of the list, comma 2, to say that I want the data in this list to go into 2 partitions, or comma 5 if you wanted to build 5 partitions because your list is much bigger. The thing to keep in mind here is that this is only really used for like prototyping and testing. If you don't want to like parallelize a really massive data set. The wrong approach here is to try to read 10 gigabytes of data from the driver JVM from your local machine's file system, reading 10 gigabytes of data, loading that into the driver JVM, and then shooting that out into the cluster. That's not the right approach. That could cause out-of-memory conditions to happen in the driver JVM. You generally, for those use cases, want to keep your data in your distributed cluster, so maybe on HDFS or on Cassandra, and then you use this other technique to read out of the distributed file system or the distributed database. So here we're reading data from not a distributed file system, but just your local ext3 or ext4 path. Notice a different method being called now, though. sc.text file, not the sc.parallelize. Using parallelize is still fine, even in a running production application, if all you're trying to do is send like a feature vector to all of your nodes. But maybe a broadcast variable would have been better there anyway. OK. So let's go back to this RDD, the log lines RDD. If this is the first RDD that you construct in your DAG, then this is usually called like the base RDD, or the input RDDs, like slang terms for what we call the first RDD. And the first RDD in here, this example, is being constructed out of HDFS. So out of HDFS, the way it works is if the file in HDFS has 4 blocks, each block feeds 1 partition. So here, we cannot control now how many partitions will be in the base RDD like you could have when you're using parallelize. The number of partitions now is being dictated by your input data source. For example, in Cassandra, the default setting is that 100,000 rows feeds 1 partition. So if your Cassandra table has 1,000,000 rows, that would imply that by default, that would give you 10 partitions. And you can tune that and say, no, only 10,000 rows in Cassandra should feed 1 partition if you have a lot of wide columns with a lot of columns, perhaps. OK, so that's log lines RDD. And the next construct and the next icon introduction is a transformation. So what we're going to do now is we're going to transform this log lines RDD into a different RDD, into a new RDD called, we're going to do a filter transformation. So there's a transformer. And we're going to call this next RDD errors RDD. We're filtering out and pulling out just the error messages. And you'll notice now we have just the error messages. This is all happening lazily. To be honest, you'll see these dotted lines around the RDD. When you make this first RDD and they do this transformation, this is all lazy. So until you actually request some results, until you actually call an action, none of this has actually happened, right? The execution engine hasn't actually computed any of this. This is just building this metadata DAG in the driver JVM. It's just building some metadata. It has not even tested to see if this file name even exists yet. It's not going to give you an error if this file name does not exist. So we're just building up some metadata, like this DAG is being built. We have this errors RDD now, and this is the same errors RDD. And maybe what we'll do next is, you notice this issue here that, see, there were no errors in this second partition in this toy example. So we ended up in this situation where this one partition actually doesn't have any content at all. So for example, now, if you do an operation on this RDD, the behavior you would see is that task 1, thread number 1, takes like, I don't know, maybe 100 milliseconds to run. But this partition, the task running on this partition, will complete in like 2 milliseconds. But it will take up a slot and then disappear off that slot in like 2 or 3 milliseconds. Right? You would have been better off if you didn't have to incur that cost of the driver having to launch that useless task. So in the lab, you will see a technique that you can use to identify this type of thing, where you might be wanting to see how many items are in each specific partition. Right? In general, you want it to be kind of equally load balanced. Anyway, when you get into this type of condition, you can use a coalesce operation and say something like coalesce 2 to bring down the number of partitions from 4 to just 2. This is kind of like squeezing or merging partitions together. And now we have a cleaned RDD. I've kind of done my ETL, perhaps, let's say, and now I'm going to call an action. I'm going to call the collect action, which is going to draw the data. All of the data in the cleaned RDD will be sent to the driver JVM when you call the collect action. So whichever machine this partition is on, that executor will ship these 3 lines or the network to the driver JVM. And wherever this partition happens to live in some other executor, that executor will ship these 2 lines to the driver as well. And then the driver will from the user interface perspective, just show you like a native collection, like a list or an array in the driver. And then you can see what the results look like. You got to be careful with collect, though, because it can cause an out-of-memory condition on the driver if you try to pull too much data into it. OK, so now that we called an action, collect, now what's going to happen is Spark is going to execute your DAG. So now the driver is going to start scheduling tasks across the executors. And you'll see how this works later. We're going to kind of dissect behind the scenes what happens here later in the class. OK, so now what's happening is now we're actually going to read those blocks. And you'll notice next we're going to go ahead and convert that dotted RDD, the dotted boundary on it, the dotted border to solid line, because now we have basically materialized this RDD. And then we do this filter transformation. You'll notice we needed 4 tasks. And we get the errors RDD. Then we get this cleaned RDD. Then we do the collect, and the actual data comes into the driver JVM. All these are considered a stage, and we'll talk about what stages are later. This is one stage of execution. And then these RDDs dematerialize. They kind of disappear. And now what you have left is the original data source and whatever data came into the driver. Right? So we never used the cache feature in Spark, so the RDDs went away. So if you look at this, DAG, the cleaned RDD, perhaps you might call the count action on it to count how many items are in it, in which case you'll see 5 in the driver. But you might call another action as well, like save to Cassandra, to save the results of those partitions into a Cassandra table. Or you might actually take that cleaned RDD and do a filter on it to filter out just error messages 1, because the downstream processing you're going to be doing is very focused on error message 1. Maybe you're trying to analyze like what's going on with this one specific error. And then you have error message 1 RDD, and then maybe you call a collect on that. You'll notice that we're using this cleaned RDD quite a bit right now. That makes a clean RDD a good candidate to cache. A kind of a naive error that beginners make is they go ahead and cache the very first RDD. So they read the data out of HDFS or S3, and then they cache it right away. And that's not maybe the best thing to do, because that might be a really large data set. It might be a petabyte of data. You're better off going in and doing some ETL to bring it down to a smaller data set that you actually will use in your processing, and then cache that smaller data set if you're going to reuse that smaller data set over and over again. So more strategically pick which RDDs in your DAG you're going to cache. So the first rule of thumb is to pick the RDD that you're going to be reusing a lot and not pick the RDD that just happens to come right away out of the input data source. And I'll give you more tips throughout the day about thinking about which ones you should cache and which ones you should not cache. OK, so if you look at the RDD graph here, what we're doing here is introducing one other terminology here. Not only is this the logged lines RDD to you from your perspective, but behind the scenes, RDDs have types. This is a Hadoop RDD. After the transformation, it becomes a filtered RDD, because the transformation you're doing was a filter. The output of a filter operation is to give users a filtered RDD. Right, so I'm just introducing that concept. I'm also introducing the fact that if the parent RDD has 4 partitions, it will require 4 threads of computation to get the next RDD. So this is the life cycle of a Spark program. You basically read some input data from an external data source, or you parallelize a collection in the driver program, and then you get the first RDD. You get the base RDD. You transform that RDD lazily using transformations like filter or a map. You cache any intermediate RDDs strategically that you want to reuse. And then you call actions like count or collect to kick off the parallel computation of the DAG, which is then optimized and executed by Spark. So here are some of the lazy transformations. They're all lazy, but here are some of the transformations. We'll cover some of these more later. Most of these transformations are element-wise, meaning like the map transformation, if you run it, in one of the partitions you have 1,000 items, it's going to pull each item out and apply the map transformation to it. However, some of these transformations work on a per partition basis. Like map partitions, for example, lets you run one method across all of, basically the way that works is imagine that what you're going to do is you want to actually take the data out of a RDD and you want to store it in a relational database, and you want to write your own code for making the connection, the RPC calls and stuff to open that. So what you might want to do here is like you might first think, okay, I'll write my function in the map transformation, and I'm going to go ahead and write my code here so that what it's going to do is when the first item out of 1,000 in that partition goes into map, it's going to go and open a connection remotely to a database, open that connection, push that one item into that connection, then close that connection, and then it'll look at the next item. Now, if you do this, you're going to overwhelm the number of open connections on your database. The better way to do this is for the entire partition, you submit a function with map partitions, and that function will be run once, and it'll open that connection once to the database, and then it'll get an iterator to the other 1,000 items in the partition, and one by one, those will flow in through that open connection to the database, and when you're done with the 1,000th item, you can close that connection to the database. And now in this case, the number of connections you would have to the database would equal the number of partitions you have in your RDD. So you still might want to be careful because it's very normal to have a healthy RDD that has 1,000 to 50,000 partitions. That's totally normal. So in that case, this is not a relevant example. If you have 50,000 partitions, you would overwhelm your relational database most likely. Was there a question? We'll cover that later in detail. I don't want to cover these in detail right now. I'm just trying to tell you there's a bunch of transformations, there's a bunch of actions. Actions just force the evaluation of the DAG. And you can see these are some of the different types of RDDs. There's a Hadoop RDD, which is the first RDD that comes out of Hadoop. When you read from HDFS, what you get is a type of RDD called a Hadoop RDD. And actually what happens in the background in Spark is automatically in the background on the Hadoop RDD, a map transformation gets run without you asking it for it to be run. So what is this magical automatic map transformation doing? Well, you know, in Hadoop, there are special data types. So for serialization, for example, in Hadoop, if you write the Java code for Hadoop, you'll notice it's not like you don't use string, you use text. You don't use integers, you use interwritable. So there's special, special data types for Hadoop that serialize more efficiently on the network. So what Spark does is when it reads those Hadoop data types, it automatically applies a map transformation to convert them to the more native Java or Scala data types. And that's what that map transformation is doing. So in your DAG, what you have already right now is even though you just read a base RDD out of HDFS, you actually have two things now. You have a Hadoop RDD, and then you have a mapped RDD as well, which got created automatically. And now the first transformation that you apply will be applied to the mapped RDD, not the Hadoop RDD. You can see this when you actually look at the DAG, or if you look at the .2debug string. Yes? You can see that, and we'll cover some of that in the UI later. OK, so there's also some other RDDs that were donated by other companies, like DataStax donated a Cassandra RDD. Esri donated a Geo RDD, so those are in green. This is the source code for on GitHub for the Scala RDD.Scala class. This is an abstract class, and the other specific RDDs are here. These are like the concrete implementations of that abstract class. So here you can see things like, this is a whole bunch of RDD. There's like a block RDD, there's a Cartesian RDD, a checkpoint RDD. There's a lot more RDDs I even had on the previous slide. Okay, another thing I want to mention that's kind of a bit advanced is RDDs have an interface. And this RDD interface is based on 5 methods that essentially capture all of the information we need to know about dependencies and about RDDs. So this is some of like the behind the scenes, like metadata type of stuff that Spark keeps track of for each RDD, for all the RDDs. All of the scheduling and execution in Spark is done based on these methods, allowing each RDD to implement its own way of computing itself and materializing itself. And indeed, users can implement custom RDDs for their own special data sources, perhaps, by overriding these functions. Okay, so all Spark RDDs are written by subclassing these interfaces. So let's look at what these are. What do RDDs know about themselves? What does the metadata they know about themselves? Well, RDDs know how many partitions they have. This is like the number of splits. So that's one thing they know about themselves. They know how many partitions they have. They know dependencies to parent. So an RDD knows who is above him. In case an RDD loses a partition because a node crashed, you lost one partition maybe, the Spark engine knows how you can recreate that partition that you lost by going to the parent. So it's important for RDD to know his parent. There's also a function to compute a given partition. You'll see what this means in a second. These are optional. Preferred locations for partitions. If you're reading out of HDFS, it'd be ideal if you construct partition 1 on the same machine where block 1 is in HDFS. Therefore, it's local read. The executor reads block 1 locally, loads it up into the executor, and there is no network transfer. So it would be nice in certain use cases to know if a partition should be materialized on a specific executor. However, if you're reading from like S3, that doesn't apply. So that's one of the reasons this is optional. And then also there's optional partitioning information. This is using a partitioner function, and by default it uses the Java partitioner, the default Java hash partitioner. What this does is if you have an RDD with key value pairs, and you repartition that RDD, then using this function is how Spark will decide, okay, key X goes to this partition over here. Key A goes to this partition. And we have another key X that goes to the same partition before. So this is basically deciding how to send the different key value pairs to different partitions based on the key. Not that much different of a concept than a partitioner in Hadoop MapReduce. Let's look at actually concrete implementations here. Here's the Hadoop RDD. So in Hadoop RDD, the number of partitions is just 1 per HDFS block. There's no dependencies to any parent RDD here. And how do you compute a partition in a Hadoop RDD? You just read the corresponding block. And preferred locations is set to be the HDFS block location. And there's no partitioner here because basically all of the data in partition 1 is just whatever was in block 1. Filtered RDD, the number of partitions is the same as the parent RDD. So if the parent RDD has 20,000 partitions and you apply a filter transformation, then the next RDD is going to have the same number of partitions. Dependencies is 1-to-1 on parent. So some RDDs, like like a joined RDD, might have dependencies to 2 parent, but not this one. How do you compute this one? You just basically compute the parent and filter it. So what that means is you just take each item out of the parent and you apply the filter transformation to see if it passes true or false for condition for the filter. Preferred locations is ask parent. So this is interesting. We are now, Spark is trying to intelligently materialize the filtered RDD so that the first partition of the filtered RDD will be materialized on the same location, the same executor where the first partition is for the RDD above it. So for partition 1 in the parent RDD, it will try to make partition 1 for the filtered RDD on the same executor, so there should be no network transfer, hopefully. but it's not a hard requirement. There's no partitioner set here. Because once again, we're not like moving things between partitions when we do a filter transformation. You know, if there's 1,000 items in the first partition, in the parent, then in the second in the second RDD, in the filtered RDD, it might be 800 items. But you're not going to move some of the data from partition 1 in the parent to some totally different partition in the child. Finally, we'll look at joined RDD. Number of partitions is 1 per reduced task. So with this one, when you do something like a joined RDD, this one is going to cause a shuffle to happen against the parent. And when you do a shuffle operation in general, you can say how many partitions you want to be to have in the next RDD. So when you do something like a joined RDD, when you do the transformation that is creating a joined RDD, and when you do this, like maybe let's say a joined transformation is what you do, then what you can say is you can say comma 15. What that means is in the next RDD that comes out of the join, I want there to be 15 partitions. You couldn't have really done that in that filter transformation, but in certain transformations that make a joined RDD, you can do this. Because what's happening now is there's a shuffle taking place, and we'll cover shuffle more in depth later, but there's a shuffle taking place. So when this happens, you can change the number of items, the number of partitions, I'm sorry. You can change the number of partitions in the next RDD. Preferred locations is none, because this is going to cause a pretty serious network, all-to-all network movement of data. So there's no optimization as far as saying I want to load my first RDD partition on this machine. That wouldn't really help you much, because in the joined RDD, the first partition is being constructed by reading maps build data from perhaps all the other executors in your cluster, are all giving a little bit of data to come into the first partition in the joined RDD. And you can see that the default partitioner is the Java hash partitioner. Yes?
Level of persistence also a property of the RDD?
No, the level of persistence is, I don't believe that's a property of the RDD. That's a different thing. Yeah. OK, so we'll take a break in just a couple of minutes. I want to mention that when you're reading from Cassandra, which is a pretty popular NoSQL database, the way you do that is like this. You say sc.cassandra table. You say which key space you want to read from, what table you're going to read, perhaps which column specifically you want to actually read, not all 10,000 columns. And you want to do a filter, you want to push a predicate push down to say only give me the rows where column 5 is blue, only those rows pass my filter. So what you're doing something here is kind of cool. This is really cool because if you can't do this when you're reading from HDFS or S3. When you're reading from HDFS or S3, the base RDD is just going to be the full HDFS file or all the data you have in that S3 bucket, perhaps. And if you didn't need all that data, then you'll do a filter operation in Spark. And then eventually you'll cache an RDD. In Cassandra, though, you can push this filter predicate down to the database layer, so Cassandra doesn't have to use its JVMs to read everything and read all the data out of all the SS tables. Instead, it can more intelligently give you only some data back. So certain special connectors to databases can do this, and this is something I just wanted to point out. And in Cassandra, if you want to not have 100,000 rows going to one partition, then you can say something like this when you start the REPL. Spark Cassandra input split size 2,000 means only 2,000 rows going to one partition. And if you're using Cassandra, I would highly recommend going to this GitHub link to check out the connector that DataStax donated to the community that is open source, and it connects Spark to Cassandra. And this is just the same thing, just some information about using this connector. OK, with that being said, it's exactly 10:30, and at exactly 10:45, we're going to continue. So I would recommend coming here a few minutes early. And I'm going to run to the restroom as well, so I'm sorry if I don't hang around the podium. But we'll continue in 15 minutes exactly, and then we'll get into some more cooler stuff. OK, let's go ahead and begin. So the general idea I had for today was not to keep it too lab heavy. This is very different than what we usually do in our training courses. The reason for that is just in a big audience like this, I think people just get more out of the lecture perhaps than sitting there and doing labs on their own. But I am going to give you some time today. I'd like to give you a little bit of time, maybe 20 minutes right now, and then maybe like 20 or 30 minutes in the afternoon to start playing around with Spark hands-on. I have a lot more labs than you'll be able to do today. However, you'll have access to the Databricks environment even after class for at least one more week after class for free, and you can do the rest of the labs then. But in designing Databricks, we took inspiration from a computer scientist, Alan Kay, when he said, simple things should be simple and complex things should be possible. So with that in mind, I'd like to do a quick demo of the user interface for Databricks. And then I'm going to go ahead and show you how to actually log in with your specific credentials. So to do this, this is not going to be quite the mind-blowing demo Ali did 2 days ago, because the goal of this is not to blow your mind, but just to introduce you to the interface of Databricks so you can be comfortable in the environment. Let's see. So I'm going to log in as an administrator to one of the 4 Databricks shards for today. So when I log in, let's see, we're going to first see like the main page, and I can see a few different things. I can see my recent items that I had open, my recent notebooks. I can create a new notebook. I can name it. I can add a library. I can run a scheduled job, or I can look at my clusters. When you log in, you're actually going to see this screen. When you log in as a first-time user, because you don't have any recent notebooks like I did. And these are just videos. Each one is like a 1 or 2 minute video to introduce you to the UI. So you can check out these videos from home. This version of Spark this is not a version of Spark. This is a version of Databricks 1.3. It doesn't exactly correlate necessarily to the Spark version. If I click on new features here, this is, you can see release notes for actual Databricks. This is, once again, not for Spark. Okay, so the first thing you'll do typically when you log into Databricks is you'll click the Navigator button. And if you go to Home, you would kind of come back to this page. But there's a workspace, there's tables, clusters, jobs, and accounts. And I'm going to begin by exploring clusters, because that's what you usually need first. You need like a cluster before you can actually do any computation. Now, under clusters, I can already see that a whole bunch of other people are logging in. This is kind of like a Google document type of interface. It's collaborative in nature. I can see other students logging in. As a student, you will not be able to add a new cluster. Only administrators have the option to add a cluster, but I'm going to add one and just kind of show you how you do this in Databricks. Let's call this, let's call it Today Cluster. And I'm going to launch a relatively big cluster here. I'm going to launch a cluster with 200 gigabytes of RAM, and that's kind of expensive, so I'm going to actually launch it as a spot instance, which can be significantly cheaper, maybe like 10% of the cost sometimes. And I'm just going to click OK. So now what's happening is if I scroll down, I should find the today's cluster. You can kind of see here that this cluster is in a pending state. Let me make this UI a little bigger as well. So you can see it's kind of in a pending state. It's starting. It's a little too big. All right, so that's going to take a few minutes to start up. But what it's essentially doing is it's right now it's launching a cluster in Amazon. If you had your own Databricks trial account, then this would be launching a cluster in your Amazon VPC. You'd be giving Databricks your some credentials for AWS, and we're launching in your VPC essentially. Yes. We'll get to that in a bit. Just hold that question. Yeah. Okay, so I want to cover what's here. The name of the cluster, how many gigabytes the cluster is in memory. Now, a 5 gig memory cluster does not imply that it can only analyze 5 gigs of data. It can analyze a lot more. It can analyze 100 gigs. It's just at one point in time, it can at most hold 5 gigabytes of data in memory. This is measured according to like the executor heap size, basically. And even in there, right, like the executor heap is not all for just RDD caching. 60% of the executor heap by default is for RDD caching. Okay, this is an on-demand cluster. It's running. This one is running. Let's see. You can also see the Spark UIs here. There's no libraries on this. There's no notebooks attached to this cluster either. We won't cover dashboards too much in this class. I can reconfigure the cluster with a few clicks. I can increase it from 5 gigs of memory to something more. I can restart a cluster if it's perhaps misbehaving, and I can terminate a cluster. It's 5 gigs in total right now. So this cluster is unique, okay? In class, the way it works is every student, you have your own mini cluster running in local mode. So everyone gets their own cluster. And the thing you can do here is you can go to this button, the Spark UI button. So if let's say I was like student 1009, in which case when I'm launching commands and actions in my notebook, I can come here and I can actually see jobs, stages, storage is after you cache an RDD, environment variables, and executors, right? This is probably very similar to what you've already been seeing in Spark. There's no job showing up because this student has not actually run anything yet on his cluster. Okay, that's all I really wanted to cover here, I think, on the clusters page. Let's see if that cluster launched yet. It's still in a pending state. So there's a lot of configuration parameters being set and optimizations happening right now. There's in the background. That should be done in really just a few more minutes. Okay, the next thing I want to cover is workspace. Actually, no, let's cover accounts next. Accounts is another button you will not have access to, but you can see here that basically every student has an account. I can reset a password, I can make a student administrator, or I can delete a user. Okay, or I can here's how you add a new account. So if you guys launch a trial, it's really a couple of clicks to add a new user. And all those users can share a cluster together. Okay, so next is workspace. In a workspace, there are 4 folders right now. You can see today's labs here under today's labs. We'll come back to this in a second. I do want to point out a few other things. Under home, every student has your own home directory. And if I am, let's say, student 1015, only this student has access to creating and doing things within this folder. As a student 1015, you cannot go into the student 1019 folder and look at those notebooks. So you have to stay within your folder. We have access control lists here and permissions done this way for a class to make it an enjoyable experience for everyone. However, when you are using Databricks in your own company, when you are working on a notebook, you can collaboratively work on that notebook with other people being in that notebook and editing cells at the same time. Okay, Databricks Guide is something I highly encourage you to explore after class. There is a wealth of information under Databricks Guide. This is the intro notebook in Databricks Guide. I can see there's a whole bunch of people coming up into this notebook right now. So this is initially this first notebook just kind of gives you some experience in the interface of Databricks and the UI. But actually, if you drill further, like you go to intro notebooks, and let's say that Python is your language of choice, this is a notebook that will introduce you to actually writing Python Spark code in a Python-based notebook. And then you can very quickly visualize it as well. Okay, I'm just going to quickly point out a few other cool things in Databricks Guide. There's a whole thing on accessing data. There's visualizations. So if you can click on, actually, I'm going to show you the D3 visualization because that's kind of cool. So one of the value adds of using a notebook-like interface is that not only can you just like start writing your code right away and not worry about the DevOps perspective of launching and configuring your cluster, but you can use display HTML as demonstrated in this notebook to visualize your RDD's information in a 3D visualization, or matplotlib or ggplot2 visualizations as well. For example, here is a notebook that covers how to use Python to do visualizations. Let's kind of skim through this really quick. So see, there's like one of the visualizations. There's another one, another one. So this is a way to kind of derive insights out of your data much more quickly than perhaps it would take in a production pipeline. We fully understand at Databricks that not everyone can run in the Amazon cloud, but we hope that you find this compelling enough to use just for prototyping and POCing, because you can do something cool, actually. We really want to make sure you never get locked in to Databricks and you're always comfortable with leaving Databricks and running this code in your own on-prem deployment if you'd like. So I will show you how to export your code out of here in just a bit. I want to also point out the Learning Spark book. And I'd like to ask, with a show of hands, how many people here have read more than 40 pages of this book? OK, I'm going to continue this question. How many people have read more than 75% of this book? OK, so that lets me gauge the audience level. Basically, about 80% of you, maybe 75% of you said you had read 40 pages, and about 25% of you said you read more, like 75%. If you have not read it, or if you still are making your way through it, all the code examples in this book are in this notebook. Here's, like, for example, the Chapter 3 Python examples. So you can basically start tampering with the examples and messing around with it and not having to rewrite all the code that you see on text in the book. Now, as you are here, you guys might be realizing that you can't mess with any of the code here. You can't actually click in here and mess with the cells. So let me show you how you do that. Let me point out that today's labs are all here. I encourage you to start with the DevOps 101 lab. And when you come here, you'll notice that this notebook is actually locked. And there's a button that I, as an administrator, have that I can unlock this notebook. So OK, it should be loading up. OK, there we go. So this is what you should do. This is the experience you'll have for today. You'll right-click this. I mean, not right-click, but just click this down arrow, then click Clone. And let's look at one of the students. Like student, what does that say? 1009? OK, so let's say I am student 1009, and I want to do the DevOps 101 lab. So I'm going to hit Clone. And I have to edit this a little bit, this path. So I'm going to just keep the first slash, and then I'm going to type in home student 1009. And yeah, I'm OK with just dropping it into root. And now, let me make sure I didn't typo anything there. I did typo that. OK, so this is the experience you'll have. You'll have to keep that first slash, home student 1009. So what happens when I do this, when I hit clone? Now, if I go into the student folder, there's the lab. Notice it's not locked. As soon as this loads up, the student can actually start clicking around in this lab. You'll notice this first cell is actually just marked down. And they're just like images, actually. But if I click around here, what the student can do now is, when you get to one of the code cells, you can mess with the code like this. You can type whatever you want, and you can hit Shift-Enter. Oh, wait, look, it says, please attach this notebook to a cluster. So the other really important thing for today is, since I'm student 1009, I'm going to connect only to my cluster, to the student cluster for cluster 1009. There we go. Now I'm actually attached to the cluster. And now I can hit Shift-Enter in this cell. And I can see that this is now running. It's executing in the driver. And I should see 11 come out as a result in just a moment. OK, so that's a cell that's running. And there you go. You saw the 11 there. And I can also then change this to like 12 and see if my computation changes. I should see 13 now, obviously. And it'll tell me like how many milliseconds or seconds the specific command took to run. This one technically took about 30 milliseconds, I believe, to run. OK, so a few other hidden things I want to show you here. in between these two cells, I can click this button, and I can get a new cell. Or I can delete a cell by hitting this. Or you can do things like this to copy a cell. And then I can paste that cell. I want to paste it here. So that's another kind of cool, maybe a hidden feature you can do. What else can I do? By the way, only a specific student. Student 1009 is the only one who can come in here. So everyone else is denied access into this folder. I can add a cell above this. I can also move a cell up or down. I can minimize a cell as well. So what happens if I minimize a cell? So let's see, I minimize this cell. It's just minimized, so it just cleans up your notebook perhaps a little bit. I can also hit lock notebook if I want to make this a static read-only copy of the notebook. Unlock. And I can also say show me results only. So essentially hide the code and show the markdown and the results, but just hide the code. This is a way of perhaps showing the notebook to an executive who only cares about the results. You can hit run all if you want to just kind of run all of these cells from the top to bottom. So what this is doing right now, it's actually, if I scroll much further down in the lab, it's actually running through. It's already done with this section. So it's basically running through all the cells from the top to the bottom. And I can see that student 1009 is probably here now, I believe. OK, so what I'm going to do next is show you a couple more things. I'm actually going to delete this notebook for the student. And student 1009, you can just kind of clone this yourself, because I've kind of messed with it a little bit already. So let me delete that. OK, other things. In here, student 1009 can make a new notebook. So maybe I want to make a new notebook, my first notebook. And I'm going to attach, once again, to the cluster 1009 only. Hit create. And now I have a blank notebook. I can go into here. And this is a brand new, fresh notebook that I can start in. A Spark context already exists. So you can just start using it with like sc.read or whatever, or sc.parallelize. OK. So that's how you create a notebook. There's other things here. We won't really cover dashboards too much today. You can add a new library like this, upload a Java or Scala jar, or a Python egg, and whatever you upload here, like will be pushed into all of the clusters in the Databricks shard. So you can add libraries. You can make new folders and subfolders. Import item is kind of cool. I do want to point this out. OK, so imagine that you've been using this for a few days. You go through all the labs, and then you're like, well, Samir told me he's going to be deleting the cluster and the shard. So what do I do? So here's what you do. You export the notebook that you want to keep. And let's see. Let me make this a little smaller. So if you click export here, you can export either to a raw source file or a Databricks Cloud Archive, which is just a zip file. If you do DBC Archive, then you can import it into another Databricks Cloud account. If you do source file, though, you will essentially just get the raw Python or Scala code. And all of the markdown will just be comments. And then what you have to do, if you want to run it in a vendor distribution, you'll have to add just a couple of lines to the very top for Spark context and Spark context configuration. And then you can just productionize that and run it in your cluster. Remember, the Spark context is given to you just like in a REPL. It comes baked into here. You'll just have to add a couple of lines if you want to run it as a script or as a pre-created Scala file. OK, so that's how you export your code out. I'm almost done. I'm about to give you access and let you do the lab. Let's see, what else I want to point out. I want to point out a couple more things. Tables. There's a SQL lab I'll show you in a second. But in tables, you can see data you can query with Spark SQL. Over here, I can see this table has 4 columns, 3 strings, and 1 big int. And I can see some sample data for the 4 columns, the genres column, and the movies ID column, the title, and the year. OK. So that's the movies table. And in the SQL lab, you do a join between all these 3 tables. This is the University of Minnesota's group lens database, the movie lens, very famous database. Okay, you can also create a new table. So maybe I want to import from Amazon, and I can just point it towards a specific bucket that has my CSV files, perhaps. I can also import data via uploading just a file, or via Databricks file system, which you can learn more about in the Databricks guide. So I can also navigate it like this. All right. What else do I? Last thing, jobs. What jobs lets you do is it lets you productionize a notebook. So I've interactively made a notebook. It looks to be working great. I want to run it every day at midnight. I'm going to make a job. I'm going to call it my midnight job. And click OK. And here's my midnight job. You can upload a jar to run or set it on a notebook. I'm going to just say, OK, my data frames lab, I guess. That is my production job for midnight. So then I'm going to click OK. So now what else is in here? I can choose which cluster I want to run it on. You can launch a new cluster or connect to my existing cluster. I'm student 1009. That is a cluster I want this to run on every midnight. And this might be a production job, so you might actually want to run this on a bigger cluster. And I've actually given you access to a much bigger cluster. If you scroll all the way down, you'll see a community cluster. It looks like the 200 gig cluster, by the way, launched already as well. But there's a community cluster of 64 gigabytes that I'm going to leave running after class. After class, I'm going to be terminating all of the individual clusters for everyone, and just a 60 gig community cluster will remain running. Anyway, actually one thing to point out about the community cluster and what is the differentiation here, well, notice here in this cluster I can see all my job IDs, but they are just these long numbers. So if everyone is using the community cluster today together, then you guys won't know when you call an action which specific job is yours. And one of the points of today is to be able to understand what's happening behind the scenes in Spark. So that's why you all have your own little tiny mini cluster. Therefore, when you go to your job, your UI for Spark, all the jobs that show up are going to be correlated to actions that you called in the notebook. But if I go to the community cluster, that's going to be like, all the different people's jobs show up in there. And in a future version of Spark's, of Databricks, when you call an action, it'll basically say your action is running job 15. And so if you go to this cluster everybody else is using, you can just go and see, oh, well, job 15 is mine. It'll be tagged, basically. OK. So we were looking at jobs. And the last thing is, OK, we're looking at the midnight job. And you can then say, I want to run it on a schedule every hour, perhaps. Or you can just do cron syntax. You guys are all developers. You can also say, under advanced, alerts. Give me an alert every time it kicks off, every time it's successful, or if it's an error. Timeout, timeout as well. You can say if this takes more, it should take no more than 20 minutes to run. But if it takes 45 minutes, then time it out, because we're hogging cluster resources of the production cluster. And you can say how many times you want the job to be retried. And you can just run it. So I'm just going to run it really quick right now. And I can see that it's running. It was launched manually. And every time it runs, you can see the other things here as well for the run. And I can see that this is actually running right now. OK, so that's all I had for jobs. And I believe that's all I really wanted to cover. This is kind of cool, actually. This is this help feature. You can say something like, let's say RDD. You want to get some help on RDD, maybe. And you can see all these different things. And if you click on one of these, it'll take you to the forums.databricks.com, which is a great resource to get some questions answered that might be more particular to Databricks. But there are a lot of Apache Spark questions here as well. But really, the best place to put Apache Spark questions is on the mailing list I pointed out earlier. But this is basically where Databricks does free tech support for our trial customers and for our initial developer customers. So we have a whole team of people who work in tech support who are always very quickly answering questions here. But like I said, this is meant to, even though there are Spark questions here, this is meant to be more of like Databricks-specific questions, and you should probably ask the more Spark-related questions in the community forum. But if somebody doesn't answer there, perhaps you can try here. You can click Ask a Question here, and you can start asking your question. OK. So I think that covers the full interface. The last thing to point out is the labs. So I recommend starting with the DevOps lab and clone that one, and then I recommend going to maybe DevOps 102. But you can also see that there's a transformations and actions lab here as well. If what you want to do is maybe brush up on what map is versus flat map, if that's what you want to do, you can basically check this out. This is actually a really cool lab that we just finished work on recently. This is showing a visual API of Spark, so you can see how to think about collect in a visual way. Here we're looking at the map transformation, filter transformation. This is inspired by an engineer named Jeff who gave us an initial idea to do this. So I'm going to cover some of these visual diagrams later. So what I encourage you to do right now is start with the DevOps 101 lab and start getting your hands a little bit dirty and getting comfortable with the environment. Clone this lab and do it. And then you can decide where you want to go next. So here is a slide to explain how the clusters work. There's how the shards work. There's 4 URLs here. And on the back of your tag, your name tag, it should say some information. It should say a few things. It should have your username and a password. The username is going to always be student and then a 4-digit number. And the password is case sensitive and it's kind of complex with like asterisks and sometimes exclamation marks in there. Now, if you're not sure which one you should be in, all you need to do is look at this. Based on the 4 digits of your username, if it's between 1000 to 1305, you're going to log into class West 03. If it's between here, you're going to go to class West 10, basically. There's 60 accounts and 60 clusters and 1 community cluster, basically, on each of these shards. If you're watching this online on YouTube, then I would encourage you to perhaps look at the Apache Spark documentation online and start getting deeper into the documentation there, because these labs are basically doing that stuff in the documentation hands-on. Here's another tip for you guys if you're here live. Spend 5 minutes maybe clicking through Databricks guide and then go through the DevOps 101 lab for about 20-30 minutes. This is not going to be enough for you to do the lab. I just want you to get your hands kind of wet, get a little bit experience, and this is going to be more homework, all these labs, really, right? Okay, so I'm going to leave you here, and in about 20 more minutes, we're going to continue with some more deeper lecture. How do you clone? You just click the down arrow next to the notebook, and then you clone, and then you have to before you even clone, you need to know your student name. So like you have to basically do this. And when you're cloning, you right-click and you do that, and then you have to change this part. And the way you'll change it, you'll basically say home/student, and then the 4-digit number. And then you can name this part of it. You can name it whatever you want, and this part is changeable in blue. So that's how you'll clone it. And then you can go into your home folder and see it. So I'll take 1 or 2 questions. If you think your question is relevant to the rest of the audience, you can go ahead and ask it now. If it's not, then just hold tight for a little bit. Yes? This is a notebook interface that was inspired by IPython Notebook because we thought that would be a great way to basically interactively work with big data and visualize it. However, this code base is a complete from scratch rewrite. It's not leveraging IPython Notebook itself. It's Markdown is Markdown, yeah. Any other questions that would be relevant to the rest of the audience? Yes. You can make a Python notebook and a Python notebook, or in the future, you'll be able to make an R notebook. Okay, yeah, you can. There's in the future there'll be an R notebook. Right now there's a SQL notebook, Python, and Scala. And in today's labs folder, there's examples of all 3 of those. For Java, you'd have to write the Java code on your computer, build a jar, and then upload it. You can do that as well. This DevOps lab is only in Python, and there's, I think, another lab later. I think it's the data frames lab is Scala. All the things in the Python lab are not teaching you Python. They're teaching you Spark. Scala has a very similar API. It's just I haven't been able to build a Scala lab yet, but it's the same thing basically. All right, I'm going to walk around in case there's any. Is there any other question that will be relevant to the rest of the audience or pertaining to Databricks? If not, I'm going to walk. Yes. Good question. After you clone it, it's going to be in your home folder. Under home, then your student folder. And remember, the first thing you'll need to do before you work with the notebook is connect it to your specific cluster. So I'm going to hang around for like another minute to see if there's any specific questions for the entire audience. If you guys are all comfortable and you're good, then I'm going to walk around and see if there's any specific questions I can answer. Yes?
Is there a way to clear the cell?
You mean you want to delete everything in the cell? Just hit Shift-A to highlight everything and then hit delete. Just the output. I'm not sure if you can clear out just the output. What I would do is just hit Shift-Enter and start going down the different cells. Yes. Actually, we'll take questions offline now, so I'm going to start walking around for a little bit. And then I want to grab some water, so I might walk out. So if you have a question, I'm going to be around for like 5 minutes, and then I'll give you guys like 10, 15 minutes to just continue doing the labs. Let me start here first. How many people are having trouble just logging into Databricks in general? Okay, that's great. I'm really happy there's only 3 hands up. Okay, I'll be walking around, but it looks like most people are in and running now.